I think as we have become aware, we are going through yet another refrigerant change. I know there's multiple people in this room have gone through one or even maybe two refrigerant changes in their time in the field. So we're going into, what would you call this, generation 4? Now, if we look at going from R12 to R22 as the interim gas to 410, and now we're moving into a whole new sort of ball of wax. We're going into from an A1, so a non-toxic, non-flammable refrigerant, into a non-toxic, mildly flammable refrigerant. And with that, there's a lot of complications, particularly on the standards. So whether it's ASHRAE standard 15, 15.2, or B52, CSA B52. So those standards had to be updated first. And they've been updated now for, well, I think we can go back to around 2022. But it took a while for the National Building Code and provincial building codes to adopt those new standards. We can say that across all provinces, that the new standards, whether it's ASHRAE 15 or 15.2 and CSA B52 2022 have been adopted. So regulatory-wise and inspection-wise, if you are purchasing an A2L piece of equipment now and today, you can safely, legally install an A2L piece of equipment. Prior to December 31st, 2024, that was not the case in British Columbia. We're only a few months into this. So I still have a lot of questions as I'm reading the standards or the updated standards and trying to interpret some of the new criteria for installation purposes. And I think it's a responsibility for us as a group to purchase the new standards and get into them and read them. And if you have inquiry questions, there are email addresses, whether it's within ASHRAE or CSA, to email their inquiries group for an interpretation, or at least to ask the question that you may not understand. And when you are asking a question or you are sending an inquiry to CSA or ASHRAE, that you have to ask them in a yes or no question, because they're not going to interpret for you and give you the answer. So you have to ask them in a manner that is a yes or a no question. Does this situation comply with, XYZ code? And they will come back with a yes or a no. Wanted to kind of go through a little bit of the timeline as, like, how did we actually get here today in the introduction of an A2L or a mildly flammable refrigerant? Well, I think we can go back to roughly the 1970s when chemists began studying the impacts of chlorofluorocarbons, or CFCs, things like R12, etc., in Earth's atmosphere, and they discovered that CFC molecules in the atmosphere were being broken down by ultraviolet radiation, causing the release of chlorine. And that chlorine was responsible for the destruction of our ozone layer. And that was, they presented a scientific paper to the House of Commons, which was backed up by NASA. Then in 1982, they came out with a global framework and a convention of the protection of the ozone layer. That leads us into the Vienna Convention, which established a framework for the negotiation of an international regulations on ozone-depleting substances, which then comes across to the Montreal Protocol. The Montreal Protocol was originally designed to create and preserve and restore the ozone layer. Okay, so that's what it was all about. And as we know, chlorine was, the contributor to the breakdown of ozone. However, so then they said, okay, we got to get rid of the CFCs and we're going to transition over to an HFC refrigerant. The issue with transitioning over to an HFC refrigerant is the global warming potential number, so the GWP number, went up. So we went from refrigerants, and I'll give you an example, R-22 had a GWP number of 1,810. They moved into R-410A, and that had a GWP number that was higher. It went up to 2,088. So they eliminated one issue, and they got rid of the chlorine in gases that were causing the depletion of the ozone layer, but they introduced another issue, and that was global warming or climate change. So a few amendments to the Montreal Protocol later, we get to the Kigali Amendment. And the Kigali Amendment is now there to address the GWP numbers. So we're now taking the GWP numbers that are, in the 1800s to the 2000s, or even as high in the refrigeration side as 3,000 or 4,000, and we're going to start to bring those down. On the heat pump, air conditioning, and dehumidification side of the story, they're bringing that number down to 700. So we're going from R-410A in our industry. We're transitioning over to either a low GWP HFC or a blend of an HFC and an HFO. And we're going to bring that number down to 700. So 700 is the new baseline. The manufacturers cannot produce a piece of equipment with a higher GWP number in the HVAC world higher than 700. What are we going to do with the existing refrigerants? We're going to go and introduce a phase down of our HFCs across the board. So what does this look like? With a baseline starting in 2013, that's our benchmark where we're going to start. So based on the Kigali Amendment, they are going to phase down the production and consumption of HFCs in steps until they get to about a 15% maintenance gas in 2036. So we've already gone through a 40% reduction of the production of HFCs. And here's another big one. This is only 4 years away. We're going to jump down, another significant amount in 2029. So when we know that supply and demand kicks in, that the price and availability of HFC type products and the gas is going to be limited, and the price is going to go up. We'll get to 2036, and this is a little bit different than a CFC. The CFCs was a phase out process. This HFC is now a phase down process. So we will always have about a 15% maintenance gas out there. That's unlike a CFC. CFCs are phased out completely, so they're no longer allowed to produce that type of gas anymore. So what does it look like on the chart, and what are they introducing today? So I put up a few different gases here, R12, and then interim gas, R22, and this is what I think we're most currently familiar with. An HFC is an A1 refrigerant comprising of, it is a blend of R32 and 125. It has a GWP number of 2,088, and it uses either a POE or a PVE oil. The two new gases that are coming into the HVAC world are going to be it's manufacturing dependent, either R-32 or R-454B. So these are the two new gases that have been introduced. A majority of the US manufacturers have chosen R-454B to be the gas of choice. So if we look at Daikin's and the Trains and the Yorks and the Carriers and then the Climate Masters and all that, a majority of them have chosen R-454B. Daikin has stuck with their R-32 as their gas of choice. So just a few examples there. R-454B is comprised of a blend, R-32, and one that you may not have heard of, but it's R-1234YF. Where that gas is most commonly seen is actually in the automotive industry. Most of your new cars, exactly. So this is an HFC and an HFO blend, okay? Their GWP numbers are both below 700. One's 675 and this one's dropped down to 466. And that drop is because of 1234YF. 1234YF has a GWP number of about 4. So it's extremely low. What's in the future? Where is the next amendment to the Montreal Protocol going to take us? We don't know. Could be down to 100, 250, we're just not quite sure. But I can say for certain that the GWP number established as 700 will be reduced. When is it going to happen? That's, again, that's up for debate. I don't know. I brought this chart in not because it has implications, well, I guess it does have implications into Canada, but the numbers that you see here, for the most part, do not affect Canadian distribution, or will it affect you as an installing contractor. So what we know is in the United States, let's just stop here. We're going to back up just slightly. Let's define product, system, and components. So we've got a product, and a product consists of either a residential or commercial, something that is packaged, okay? Something that is all connected, all in one, requires essentially no a field assembly of the refrigeration circuit. A system, let's call that a ductless split or a unitary split with a heat pump and a furnace and an air handler, something along those lines, something that does require assembly. So that's classified as a system. And then we have components. Components are repair things. So if you had an A1 piece of equipment out in the field and it required repair, you can still purchase, and manufacturing is going to continue to produce coils, reversing valves, compressors for our A1 type products, so our HFC products, our R-410A products, okay? That's never going away. We're always going to be able to repair it. But let's go back to products. The United States stopped producing R-410 or A1 type products, HFC type products, on December 31st, 2024. They no longer manufacture it. They have all transitioned their lines over to produce A2L type equipment. I say this quite a little bit facetiously. The trade between Canada and the US has traditionally been relatively strong. That might be up for a bit of a debate currently, but because Canada trade relation with the United States has been so integral over the last decades, Canada was heavily reliant on US production, US manufacturing. So since the United States stopped producing A1 type equipment, that affects us greatly. We do not, these laws and requirements are not part of Canadian manufacturing. So if a Canadian manufacturer is still producing an A1 or R-410A piece of equipment, they still can by rules, laws, and regulations. This is only down in the US. But considering that we purchase most of our equipment from the United States, and since they stopped producing it on December 31st, 2024, that has a huge impact on our industry. Okay, so products. The US stopped producing it last year, but if they have it in their warehouse, you can still purchase it and you can still sell it for the next 3 years. So if they have a rooftop unit down there and it's still in their warehouse, they can continue to install it for the next 3 years. Systems has a 1-year sell-through. Okay, so they have about another 8 months left. Components, never going to stop building it, etc. So I bring that up because you may see this online or from another manufacturer, and you think, oh my gosh, you know, a Canadian distribution, I can't get this equipment anymore. Well, that is sort of true. I might not be able to sell it. Yes, you can. Now I want us to take a look at the flammability side. I have been led aware, and I have gone online, and for clickbait reasons, purposes, through either of it's YouTube or Instagram or something like that, and you type in to your little search engine A2L flammable refrigerant, right, into YouTube. Okay, try it, because you'll be amazed at what you find. You'll find a person working on an outdoor unit, and there will be a massive explosion and fire. You will see situations and videos all over the internet about A2L refrigerants catching on fire, having mass explosions, and what do we do with that? We send it to our buddies. Hey, check this out. This R-32 piece of equipment, just saw it on YouTube, and you're going to install it at your neighbor's house. It just blew up. Okay? I want to take a look at the flammability side of an A2L refrigerant and try to diffuse that conversation, because A2L refrigerants just cannot do what the internet says, or internet is showing us that it is capable of. So we're going to take a look at 4 different areas on how ASHRAE 34 classifies the flammability side of refrigerants. We're going to take a look at the upper and lower flammability limit, the minimum ignition energy, so that's the amount of energy or heat that it's going to take to light a fuel. The heat of combustion, so that's how much heat is contained within a certain weight of a gas. And its burn velocity. So how do they test it? They take a gas and they mix it with air. They put it inside a beaker, and there is an ignition source in the center of that beaker. And they try to light it, okay? So what they're going to do is, based on the flame spread beyond this 90-degree sort of window in here, so based on the flame spread beyond 90 degrees, as well as the flame speed, defines the flammability. So flame spread that is less than, so if it's inside this 90-degree window, equals no flame propagation, okay? So there's one portion of it. Flame spread beyond 90-degree window, R-410A, R-410A is just inside. A2L refrigerants, look where R-410A was, and look where R-454 and R-32 is. It just got outside that window. So very, very narrowly just made it outside. Propane, obviously, that's an A3 refrigerant. Very flammable, very explosive, as we know, and it's very easy to ignite. So flame spread beyond indicates that it does have flammability. So now we have to define that flammability a little bit further. And that's the definition, as well as flame speed. So we know it went outside it, but how fast did it get out there is another part of the classification. So if we take a look at ASHRAE 34's refrigerant classification chart, I think we're all relatively familiar with this. A, or the letter, is the toxicity, so A is a non-toxic, B is a toxic refrigerant, and then the number indicates its flammability. So 1 is a non-flammable, 2 propagates flame, and 3 exhibits extreme flame propagation. So let's take a look at this. Let's look at this. Is a little bit easier, color-wise. Exhibits flame propagation at atmospheric pressure, 14.7 psi, what we're sitting in right now, at 140 degrees. So there's our baseline. That's where all these gases are tested at. The lower flammability limit, being that it is greater than, and now this is in pounds per piece. So this is how much refrigerant is in a pound of air. So 0.006242 pounds of refrigerant in 1 cubic foot of volume. Or you can multiply that by 1,000 to make it a little bit easier. So that'd be 6.2 pounds of refrigerant in 1,000 cubic feet of volume. So that's an A2. And then we've got heat of combustion. So heat of combustion is less than 8,068 BTUs per pound. Okay, compare that to something like propane, which is about 2,500 BTUs per pound. Now, you'll notice here between a A2 and an A2L, an A1 has no flame propagation, right? Because it was inside that 90-degree window. Okay, so no flame propagation there. So what are we looking at now? These numbers here are all exactly the same. The lower flammability limit between a 2 and a 2L, heat and combustion is also the same. So the only difference between a 2 and a 2L is its burn velocity, being that it is less than 10 centimeters per second. That's the only difference between an A2 and an A2L. 10 centimeters per second. How fast am I walking right now? Just about that, okay? The average human walking speed, you're walking down the seawall, is about 60 to 70 centimeters per second. So if you had a flame speed that is less than 10 centimeters per second, and Gary, if you were the ignition source and this room was full of an A2L refrigerant, and you were the ignition source, and we're within a proper gas and air mixture, so we could sustain combustion, okay? You're the ignition source. Well, there's a candle there, so let's go from the candle. To me, it's traveling from that candle towards me at 10 centimeters per second. I could probably get on the ground and crawl or roll away faster than that flame could travel towards me. So these explosive events that we're seeing on clickbait, YouTube, etc. are almost an impossibility. Lower flammability and upper flammability limit. The LFL represents the minimum concentration of refrigerant in air required to ignite or to burn. And the UFL, or the upper flammability, becomes, to make sure that it's too rich for it to burn. So 0% gas, 100% air, all the way to the opposite side. So now it's pure gas and no air. So like a jug of refrigerant is obviously on this side. Right now, we are in the 0 gas, 100% air. This is an example of R-454. The LFL is 11%, so on the low side of things. And the UFL is 22%. So you have to have a gas-air mixture between 11 and 22% for this R-454 to be combustible, okay? R-32 is 14 and 29%. So it just moves over here just slightly. It's about the same window, but just moved over just ever so slightly, okay? This is a really important thing to know and understand because it ties in with how a refrigerant leak detection system works. So just remember this LFL number here for a moment until we get into how an RDS system works. So we got too rich and too lean. We know in a natural gas or propane furnace, of course, if it gets too rich, it starts to burn very carbony to the point where you can't even ignite it. Minimum ignition energy. The MIE is the minimum electrical spark energy measured in millijoules required to ignite a flammable gas or air mixture. Okay, so we got to be able to light something, so it has to have a certain amount of energy to light a gas on, to light a fuel. As a reference point here, anybody familiar with automobiles, they all have spark plug. Well, unless you're diesel, but for an automotive spark plug, just take a note here that an automotive spark plug has an ignition energy of around 20 to 30 millijoules. And anybody who has the misfortune to be electrocuted by a car spark plug knows that it hurts and it'll jump a gap that is an inch to an inch and a half. There's some serious energy behind that. So most A2L refrigerants are difficult to ignite because they have a very high minimum ignition energy, meaning that they're very difficult to light because it takes a tremendous amount of heat or energy to light them. And they've also made the statement that most, common things in your house, hair dryers, these small electrical sparks, static electricity, on-off switches, there's not enough energy in that to light that fuel, okay? Heated combustion. Heated combustion is the measurement of the amount of heat released on a substance in the case when it is burning. So we take a volume of a gas-air mixture and we burn it. We measure how many BTUs that it comes out of that volume of gas. Okay, A2L refrigerants have a much lower heated combustion than A3. So comparing that to a propane, it's around 25,000 BTUs per pound, right? I think it's a pretty familiar number. A2L refrigerants, remember that classification had to be less than 8,600 BTUs per pound. And if you do get to have an A2L ignition or an event, there's almost not enough heat in it to catch something else on fire, like a tablecloth or paper, because it just doesn't have enough heat to do it. And then burn velocity. Burn velocity is the rate in which a flame front, okay, so that's that flame traveling through a gas and air mixture in front of itself. It's propagating towards yourself, Dave, there. So we can look at it like, and again, here's that same number. It has a flame speed that is less than 10 centimeters per second. So I put a little bit of an eye chart here together using some of the common gases we've got. So we've got A1, right, 410 we've been working with for the last decade, R-32 and R-454B. So those are the gases that we are moving into. And then 1234YF, and then we have ammonia and propane. Okay, so let's just take a quick look. What do we got here? This is where I'm interested in. Let's take a look at R-32 and R-454B's minimum ignition energy. And remember, go back to that car spark plug. 20 to 30 millijoules of energy is where a car spark plug is kind of at. That's substantial. R-454B takes between 100 to 300 millijoules of energy to light it. That is essentially an open flame. There's no spark out there in that sort of range. I guess on the low side of R-32, it's really strong, like a seriously strong spark. You could get that to light. And then there's heated combustion, 3,000, 4,000 BTUs per pound. That's not much. That's not a lot of heat. And then the last one here that I think is, really telling is their flame speed. We're talking 5 centimeters a second. Remember, a human walking speed is 60 to 70 centimeters per second. So if you if you were A2L, I'm escaping you. So the chance of an explosion with an A2L refrigerant is low. Anyway, I think this is really an interesting thing to look at and compare other gases to an A2L and have a real serious kind of look at it. And okay, that YouTube video that I saw online or my buddy sent to me, now that I kind of see this and I kind of understand it, do we think that's even possible now? No. Okay. Moving on into AHRI, guidelines M and N. Guideline N is what defines our refrigerant cylinders. So, our cylinders traditionally, and it also defines the color coding of our cylinders. So what do we have? We have green cylinders for R-22 and blues for some of the 500 series. And of course we had rose for R-410A. AHRI is stepping away from color coding our refrigerant bottles. We've got so many different refrigerant blends or refrigerants and blends out there that they have essentially running out of colors and color combinations. So you are going to see moving forward a majority of our cylinders are going to come out as this, but they're calling it a gray-green color. Your cylinders are going to be sort of a gray-green color. A2L cylinders are going to have a red stripe or a red top to them. The cylinders will also have a pressure relief valve in them rather than a burst disc. For obvious reasons, we would rather burp off that pressure than a burst disc, releasing in a small volume, say your van. And then Guideline M defines the fittings that are going to be on our tanks. So no longer are our tanks going to be right-hand thread. A2L cylinders will be a left-hand thread, and there's going to be two different adapter sizes. So any tanks less than 50 pounds will have a compressed gas association number 164 left-hand quarter-inch thread on our tanks. 50 pounds and larger, compressed gas association number 670 is going to have this 3-piece left-hand thread adapter. I'll just make anybody purchasing a cylinder that is 50 pounds and larger, ensure that you don't forget this on your quoting purposes, because this little guy, it's $100 and a half. It's a pricey little beast. So please don't forget it. They are expensive. This is in the $20-$25 market. It's not much. But also take a look, here. You can help define or identify what has a left-hand thread versus a right-hand thread with these 3 knurls. So a right-hand thread adapter or connection will be knurled all the way through. Anything left-hand thread will have 3 little knurls to it. So that's a quick way. You're rooting through the stuff in your vehicle, and you're like, oh, there it is. There's the 3 knurls. Okay. So all tanks, left-hand thread, whether if it's going to be 164 or 670. Okay, now we get into some of the safety side. So we got Underwriters Laboratory 60335-2-40. So that's air conditioners, heat pumps, and dehumidifiers. So that's the safety standards behind it. Leads us into the refrigerant leak detection system. And it also leads us into effective dispersal volume charge. So those are 2 really big topics that is newish into our industry, because this effective dispersal volume charge is very similar to an RCL, so the refrigerant concentration limit. UL, as we know, is a safety standard. Now, if we kind of go back in a little bit of history there, we have and we kind of try to tie this all together. What do we got? We have manufacturing, okay? We have the chemists, and we have, let's call it like the Kigali Amendment. So the Kigali Amendment says we need to get down to a GWP that is lower than 700, okay? So that's what came out of the Kigali Amendment. So then they go to manufacturing and the chemists, and they say, okay, we need gases that have a GWP number that is less than 700. Chemist, what do you have available for us? The Chemours and the Honeywells of the world, they say, okay, we've got this list of gases, and let's say they gave them a dozen different blends and gases to choose from. And they give those to the manufacturers, and the manufacturers now start testing those gases that the chemists have given them. And then the manufacturers realize that, hey, and the chemists realize that, hey, the only gases that work and the only gases that are available are mildly flammable. Okay, so now the chemists and that side of the industry, manufacturing, has identified that 2L refrigerants are the only refrigerants that are less than 700 and also meet all the criteria for oil return and net refrigeration effect and efficiencies and all that kind of stuff. So they said, okay, now we're changing from a non-flammable gas to a mildly flammable gas. Now that gets the attention, of course, of the safety side of the story. So now UL gets involved. So now Underwriter Laboratories says, well, if you got an air conditioner or a heat pump or a dehumidifier, we need to do something because it's if you have a leak, it could become dangerous. So they said a refrigerant leak detection system that senses a loss of pressure is a critical component in mitigating a risk. Because they do, let's see, back up here. One of the risks associated with a household heat pump, air conditioner, or dehumidifiers is a refrigerant leak, okay? So they said if you have a leak, we need to be able to test for that leak. So they come up and say, well, an RDS system that must be installed that senses a loss of refrigerant pressure to mitigate that risk, okay? And is required for all systems in an occupied space that precedes a prescribed refrigerant charge. So there's the UL's statement. Anything that is less than 4 pounds is exempt. So small ductless splits, little portable air conditioners, stuff like that, they're exempt. It's less than 4 pounds of charge. So a refrigerant leak detection systems are required to have a both sensor and a control logic to activate an evaporator fan. And why are they activating a fan? Well, it goes back to that LFL number. So if you have a leak in your system somewhere and it's leaking into your evaporator coil, into your ductwork, into your human occupied space, the best thing to do is to try to dilute that refrigerant to below the LFL number. So if it is flammable at 11%, as what we saw with R-454B, okay, the detector is going to detect that at 25% of the LFL for that prescribed gas. So to simplify that a little bit, let's call it 10% LFL. That's going to give us an LFL number that is 2.5%. So I'm going to activate my alarm at 2.5%. So it's never going to be flammable. I'm going to turn on a fan and I'm going to dilute that refrigerant. 240 also is going to limit the refrigerant charge that I can release into an occupied space. So if I have a 10-ton rooftop, no, let's call it a 5-ton rooftop unit serving this space, that 5-ton rooftop unit is going to have a refrigerant charge in it, somewhere between 6 to 8 pounds of refrigerant. Can I safely release that entire charge into this space and still be below the LFL number? And there is math to look at and to do that. So the way that the RDS system works, as I described, works by eliminating one of or changing one of the requirements to support combustion. So oxygen, refrigerant leak, and an ignition source. So if I have a refrigerant leak, if I take away any one of these, I can no longer have flame or fire, right? If I have a leak, but I don't have any air, I can't have fire. If I have a leak and I don't have anything to light that refrigerant on fire, I can't have fire. So this is the beginnings of how that refrigerant leak detection system works. You have a leak, well, I'm going to change that gas and air mixture by moving air across it. So UL 240 says, now they don't define the technology to be used by manufacturing on how to develop an RDS system. What they did is they gave the manufacturing world guidelines on what an RDS system is to be comprised of. So they said, well, you have to be able to you have to have an element, you have to have something there to detect refrigerant. Okay, so there's the start. And then that element must be able to communicate some way to a sensor, some sort of logic, some sort of control board. And then that sensor, now these two are obviously typically combined together. Okay, now that sensor has to be able to send out a signal that it has detected a gas. Okay, now that signal, whether that be volts DC, resistance, pulse width modulation, communicate, or pardon me, like computer language, not defined. It just says that I have to be able to take that information and I have to get it to the RDS controller. So the RDS controller is, as a circuit board, and it's going to have logic built into it to tell the equipment to do something. Okay, so we've got an element, we've got a pack of relays, and then that pack of relays is going to tell the system or the product or the furnace to do something. So in this case, what is it actually going to end up doing? So in the event of a leak, sensor is going to pick it up, and it's going to pick it up at 25% of LFL, okay? Because we don't want to pick it up while it's already in the area where it can combust. We have to detect it before that. So we pick up that gas, we send the signal to the RDS controller itself, and then the RDS controller turns everything off. Heat, cooling, thermostat if it's a non-communicating system. If it's a communicating system, the thermostat stays on, but you will get an error code at the thermostat, so your customer in a non-communicating 24-volt world will just notice that the thermostat has gone dead. Okay? Heat turns off, air conditioning turns off. And it turns the it turns the blower motor on. Okay? The blower motor turns on to dilute that gas. So when the event is over, everything goes back to essentially normal. Whether the fan was on or off doesn't matter, but you will now have full system operation. This must activate this within 30 seconds, and the fan, by UL standards, must run for a minimum of 5 minutes. Most manufacturers are more than 5 minutes, but the fan must run for a minimum of 5 minutes to dilute that air. And again, once that detector no longer detects a gas, it will turn everything back on, back to normal again. Any questions on this piece? Because this is how the RDS system in our residential and commercial rooftop unit, it works. There are two different versions. Sorry about that. There are two different versions. This is a kit version. So if it is a legacy style, so it's an A1 older style furnace or air handler, you can purchase a separate kit to integrate into your equipment. If it is A2L compliant, the circuit board is going to be integral. It's going to have it's going to have the sensor pre-installed, and yeah, and then there's communicating versions, there's non-communicating versions. Every manufacturer is designing their RDS system around UL's guidelines, so they're all going to have the same basics. This is that uses thermal conductivity of the gas. That's just this one supplier. There may be other methods for detecting refrigerant in the gas and air mixture. Sensors are proprietary to that manufacturer or that RDS system. On the maintenance side, again, I just took this straight out of a manufacturer's installation manual for an RDS system, and they are recommending that it be checked once every 6 months, so it's like spring and fall type. Maintenance-wise, they're really not saying much other than keep it clean and free of debris around its sort of like sensing port, I guess. Don't wash it, don't get it wet, don't, try to blow it out with high pressure air or nitrogen. Really, they are just saying keep it dust free and clear and open. Because these sensors are typically mounted right up against the indoor unit's evaporator, there could be subject to getting wet. It could be subject to frost or a frozen up coil. In those cases, in those those examples, the sensor must be replaced. Okay, there's nothing else to it than that. They do not need to be sent away for calibration or have a calibrating gas to check their calibration. As a part of UL, they have established some pretty interesting guidelines for that sensor and things like its lifespan and things like decay. So is the sensor as good as it was on day one as it is 10 years from now? So they have built in things like decay. They have built into the RDS controller to test the sensor for functionality and come up with error codes if the sensor has failed or is out of its own calibration. If the sensor does fail, its default logic is to turn the entire system off and turn your blower motor on. So that's its kind of default to safety. Anything else in there on the sensor? I can't think of anything off the top of my head. And again, this is just one example from a manufacturer. Every manufacturer is going to have their own. The design and the functionality, again, has been laid out by UL. So it's all going to have a base functionality. They may have a few different bells and whistles to them. Error code wise, they do have this one has a little LED light on it that says, hey, I'm flashing green, I'm initializing. If detected, it's going to flash. In this case, it's going to flash a blue light. There's a lot on the RDS controller itself. Whatever manufacturer that you are working with, one of the first things that I would do is I'd grab their install manual, maybe contact their tech support persons, whoever they are, and have a discussion about all the intricate workings of their particular brand, right? Because they're all going to be slightly different. There's one other note that I wanted to bring up here. This one down here, these green little 3 screws, or that plug, is zone control, or for zoning. In the event of a gas and a pickup and the activation of this, fan on, all dampers open. Okay, it's going to drive all of our dampers open. Now, so let's move into effective dispersal volume charge. This is very similar to the refrigerant concentration limit. We've always had an RCL number out there. Comes into play more often with a VRF system. So in a VRF system, I think we can imagine a large, let's call it a 20-ton condenser, and then a bunch of small heads in small offices. Obviously, the charge in that system is very large, right? Let's call it a 50, 60-pound charge in a system like that. And we've got a bunch of 7,000 BTU heads in small offices. Well, you can ask yourself, well, what happens if that it splits a liquid line in a small office, right? We're going to dump the 50, 60-pound charge into a small office. So the RCL number for R-410A is 25 pounds per 1,000 cubic feet. So the effective dispersal volume charge is very similar to RCL, but we're now referring to A2Ls, okay? And it's not asphyxiation that we're concerned about. It's, of course, the flammability side. So there's some math behind this. You can find the math for all the various different types of systems in ASHRAE 15 or B52. So this is the maximum refrigerant charge of any independent. Okay, so let's take that as a question. Independent meaning if you had a 10-ton rooftop unit and it had 2 5-ton refrigeration circuits in that 10-ton unit, you're only having to do the math for a 5-ton circuit, not for both. Because if it has a leak, typically it's only going to leak on one of those 2 circuits. Again, 5-ton rooftop unit here, if it leaks and dumps that 7 pounds into this space, am I in compliance or am I not in compliance? Is that safe or is that unsafe? That's where this comes into play. And it is calculated using the volume available. So this is the volume that's available to dump that 5-6 pounds charge into. Okay. You'll find that in ASHRAE 15 and 15.2. You'll also find that in CSA B52 2022. So those are the newest standards. This flow chart I created from ASHRAE 15.2 because we need to take a look at where do, if I'm installing a system, what codes apply within that standard. So in the flow chart, it's very similar to ASHRAE and B52. They have very similar flow charts. We have to ask ourselves a series of questions to get to what codes apply. So the first set of questions you have to ask is determining the occupancy classification. Is this a residential, a commercial, institutional, or industrial space, etc.? We have to ask that question first. Then I need to look at determine the refrigerant system classification. What is it? Is it direct, double direct, or indirect? So direct would be a rooftop unit, right? A condenser, an evaporator, and a compressor. Double direct would be like a cascade system, one evaporator feeding into another condenser with multiple compressors, cascading down to like an ultra temp low freezer, things like that. Indirect would be something like a chiller, a chiller plant, machine room, chilling a brine. That brine is now going to, do something else in a cold storage plant or an ice rink or something, okay? And then we have leakage probability. Is it a high probability or low probability? And what does that mean? So high probability, what this is referring to is if you have a leak in your system, is it have a high probability getting into a human-occupied space. Rooftop unit, if it leaks, it's going to get into the ductwork and it's going to come into a space like this. That's high probability. Low probability might be like a machine room, a chiller in a machine room, not for human comfort. If it leaks, machine rooms have their own set of criteria. Then what type of gas are we working on, A1 or A2? And then the system identification and application. So refrigerant system for high probability human comfort or for something else besides human comfort. So food storage, things like that. So for an example, now there are so many examples, you would take months to go through them all. I'm going to give you one, is a space very similar to this. So it's commercial, direct, where you use a rooftop unit, and an A2L, so it's a refrigeration system and it's a high probability for human comfort. And the example that I've created was, again, a 5-ton rooftop unit serving a space like this. I have taken the volume and I've made it a 40 by 12 foot space, so it's something about this big. The charge of this rooftop unit has a 6-pound refrigerant charge. We're using R-454B, okay? So ASHRAE has the math behind this, so does B52, and every different situation has a different math behind it and charts and stuff to go by. So VRF, a water source heat pump, right? Because a water source heat pump does not have a fan to dilute your refrigerant if it leaks. So that has a bit of a different set of math behind it. So math-wise, the effective dispersal volume charge is equal to the volume, so the effective volume, that's this space here, times the LFL of the refrigerant. And now this is R-454B, so that's 0.0185 pounds per cubic foot. And there's a correction factor, and then this last one is for occupancy classification. So we looked at the occupancy classification here, residential, commercial, industrial, institutional. Institutional has the highest set of safety standards for obvious reasons. If you're in a hospital and you're incapacitated and there is a leak, we want that system designed to be the safest possible. So it has a higher safety standard. All other systems use a factor of 1. Institutional uses a factor of 0.5, so that makes it twice as safe. So when we do the math, we take the volume, 40 by 40 by 12, we get 19,000 cubic feet. We multiply that by the LFL of the refrigerant, which you can find in ASHRAE 34. We multiply it by correction factor and its occupancy classification, and we come out with 177 pounds. So in a 40 by 40 by 12 foot space, we can safely disperse 177 pounds of refrigerant into this space. The charge on this system was 6 pounds. So is it in compliance or not? It's in compliance. And it's in compliance by a long shot. Okay? Here's another way to look at this. Most manufacturers have come out with a table in their installation manuals that simplifies so we don't actually have to do the math behind it. So this is called a TA min table. This came out of one of the manufacturer that we work with out of, I don't know, it was a split outdoor unit, 13 SEER, 14 SEER, whatever it was. And the way this TA min table works is they've given us pounds of refrigerant, and you can safely disperse that 10-pound refrigerant into a square foot area of 149 square feet. Okay? So a 10-pound charge in a system can be safely dispersed into 149 square feet of area. Notice that it's square feet, not volume. So they've taken some assumptions there, and it's based on an 8-foot ceiling. Okay. But we can also take a look at this and imagine what a 10-ton split actually is, right? That's about a maybe 3.5 ton split heat pump or split air conditioner. And I'm serving a space that's, a 10-foot by 15-foot room. Now, there's no load that I can think of for human occupancy that is a 10-foot by 10 or 10-foot by 15-foot room that requires a 3.5 ton load. I can think of things like server rooms and transformer rooms, stuff like that with all sensible heat. That's where I can see this. But what it is saying is you can effectively disperse a fair amount of refrigerant into a small space.
But what if you had a multi-split, so everything's connected to a 3-ton unit?
Multi-split.
Like,
okay, yeah.
Can't all that refrigerant come out of one head if you have a leak in that one head?
Yeah, absolutely. So when it gets out of compliance, then you have to take a look at doing things like making that area larger. So, yeah, right? But so let's make the area larger. So if you had a multi-split and you had a 1-ton, 1-ton, and a 1-ton, and they're all serving small rooms, you can do things like add permanent ventilation. Or a permanent opening into a wall, or undercutting doors. And ASHRAE 15 allows for the math to go behind adding permanent ventilation into a space.
But you would have to calculate your area based on the full capacity of your outdoor unit.
That's right. So
it wouldn't be just whatever size head you.
No, that's absolutely correct. So if that multi-split had, let's say, 10 pounds of refrigerant in it, and you could effectively disperse, let's say you were out of compliance by 2 pounds, okay, into that space. You have to do the math on 2 pounds of free area and connect that free area into another space. So if your other room was, another 500 square feet, the whole size that you have to create would only be on that 2 pounds of out of compliance gas rather than the whole charge. There are other methods to do things like a multi-zone, and it could be attached to, rather than dispersal into a different space. You could do, now, manufacturer-specific isolation valves. The isolation valve scenario would have to be from the manufacturer. You can't install third-party. It had to be certified with it. So in the event of a gas leak, you shut off your liquid line, vapor line. Now you only have to do the math on the weight of refrigerant between the isolation valve and your indoor head. There's a lot of variables out there. But it's all about either creating more space by connecting other rooms together, or doing things like isolation valves or permanent ventilation or mechanical ventilation. So there are rules and guidelines out there for all of those. So the other part about, when you're doing these third-party sort of designs, like system buildups, is ASHRAE allows for you to do a system buildup. Okay, so you're designing and building your own system, and then you're going to be able to mount your own refrigerant detection system somewhere, so your sensor, and they give you the instructions to put it. They just say, put your sensor into an area where it's most likely to accumulate. Right? That's, I think, the wordage that they use. Okay, so there's quite a bit in ASHRAE 15 to look at and dig into around all of the other systems that you're going through your head right now, and all the systems that you work on, and all the ones that you're thinking of, is that there are solutions and there is math behind, if you're in compliance, if you're out of compliance, if, I got too much refrigerant, how do I mitigate that? How do I, expand into other rooms? It's all there. We only have an hour and a bit to kind of discuss this. We could talk about effective dispersal volume for each one of these systems for hours and hours. But yeah, right? So there's other things in UL 240. We're going to mitigate ignition sources. So you'll find things like compressor contactors are now hermetically sealed. So if you're replacing it, it has to go with something that is compatible with it. All of our connection points in a system is going to be identified by red. Whether it be tubes, sleeves, paint, or caps, they're going to have a red identification. Connection to a system is still going to be a 1/4 inch standard right-hand thread. You're going to find lots of warning labels, go fast stickers on our new equipment. And then anything that requires an additional system charge, you are been instructed to handwrite your total system charge. So if you've got a 5-pound charge, you have to add a little bit extra gas because of a long line set, you'll have to write that down. On the installation side of things, if you're doing good practices today, very little has changed. Always refer to your specific manufacturer's installation instructions. And of course, at the end of the day, authority having jurisdiction, overrides all of this. Refrigerant piping using A2L equipment is subject to leak testing and evacuation requirements. So there are some new codes about leak testing and pressure testing that you'll have to adhere to. Line sizing is very similar, if not virtually exactly the same as R-410A, whether if it's R-32 or R-454B. If your current line set sizing, what you're familiar with, A2Ls are very similar. So we're not going to have to upsize or downsize. Brazing-wise and making our connection, it is okay to use either press or mechanical style fittings with A2L refrigerants, and as well as brazing, of course. I took a couple of really big ones out of ASHRAE and B52, things that are new. So when you're installing A2L refrigeration piping, it must be protected by shield plates or strike plates. And of course, there are some prescribed distances. So that's within 1.5 inches of an outside wall, or if it's a floor plate or ceiling plate, it's 2 inches. So if it's within those, you'll have to install strike plates. Reusing old pipe has the same rules and regulations that new pipe does. So it says, basically if you're reusing existing pipe, that pipe shall be protected, and you must be able to prove that it's protected in the event of an inspection. So be aware that yes, you can reuse your old, A1 piping when replacing a system. Prohibited locations for A2L piping are places, obviously, all of safety. So you cannot run any exposed A2L piping in anything safety corridor-wise, okay? So you can dig into those codes in ASHRAE and B52 for more info. Piping shafts, this is a real big one. that if you have a piping network and you are penetrating 2 or more floors going vertical, that enclosure, that pipe must be installed in a fire-rated enclosure. So that's 2 stories or more. And that's only if there are joints in that vertical shaft. Okay, so if it's one continuous piece of pipe from the bottom to the third, okay, then you don't have to. If there are joints into it, then it has to be in a fireproofed enclosure. And then you are going to have to ventilate that enclosure as well, whether it be natural or mechanical. And then ASHRAE will prescribe further your minimum ventilation requirements, mechanical or natural. Recovery, if you are opening up an existing system, they're asking you to sweep by purging dry nitrogen through that system before cutting it open or recovering it. And that's just to get any A2L, slightly mildly flammable refrigerants out of there before you open your system up. Pressure testing requirements. You are now required to pressure test and document and save those documentations in your startup reports. And you must pressure test it for a minimum of 60 minutes at its designed high pressure. Okay. And following your pressure test, you must also perform a vacuum test on a system. So that's pulling it down to 500 microns. And you must also do a decay test that must last for 10 minutes, and it shall not rise more than 1500 microns. Those are all new requirements in ASHRAE. Okay. And again, I go back to if you're doing good installation practices today, very little has changed. Okay, charging and glide. I will very kind of quickly going over this here. R-454, as we saw, is a blend. It's comprised of R-32 and 1234YF, and there is a small amount of temperature glide to it. Okay, so there's around a 2 to 2.5 degrees of glide to this refrigerant. So when you are calculating or performing your superheat calculations or your subcooling calculations, ensure that you are using the appropriate column. I'll go back here 2 slides. For subcooling, you're going to use your bubble point or your liquid pressure column. Okay. For superheat, you're going to use your dew point or your vapor pressure column, depending on which PT chart that you're using. So, again, dew point, superheat, vapor pressure, use the right column. If you accidentally use the wrong column while performing your superheat calculations, there's not a lot of impact. You don't make too many decisions with a TX valve operated decision on, if you're going to be out by 2 degrees, right? If I use the wrong column here, that's either going to go up to 12, 13, 14. I'm not going to make a lot of decisions based on that, but you might make some decisions if I'm out by 2 or 3 degrees on your subcooling side. If you accidentally use the wrong column, right? Maybe I've got too much refrigerant in there, or maybe I have to recover some. So there are some decisions made here. So again, use your liquid pressure or and then your homeowner's manuals. You've got them now. It's required by ASHRAE to leave those on site. I guess before, the previous version of this, you didn't have to, but now it is required. So then very lastly, we get to take a look at our tools. What existing tools you're using today, for the most part, you can use with our A2Ls. Maybe with the exception of our recovery unit, it must be A2L certified. A vacuum pump is a vacuum pump, but the vacuum pump, A2L certified vacuum pumps do have hermetically sealed switches in them for arcs and things like that. You'll also notice that any A2L equipment, so a vacuum pump or recovery machine, now has a 3-meter long cord to it to get the disconnection point further away from your tool. Manifold, your current gauge set is the same, right? If you're just measuring pressure, you're just measuring pressures. Let's see, recovery cylinders, we already spoke about that. Ventilation required. Leak detectors, if it's capable of R-410A and R-22 and 12 today, then yes, you can use it for A2Ls moving forward. So you don't have to replace that one. So if it is HFC capable, then yes, you're good. And these are the resources where I would recommend that you purchase some standards here to get yourself familiar. Obviously, CSA B52 2023 is the most current CSA standard. You just go to CSA website and purchase it there online. You can get a paper version or a PDF copy. And then ASHRAE 15 is a new standard from ASHRAE. ASHRAE 15 is on the commercial side of things. 15.2 refers to the residential side of ASHRAE 15. And then ASHRAE 34 is an interesting one because it all has to do with refrigerants. And you can buy these three as a package for about $250 to $300. That's about $150. And those, again, they're about $150 each. So if I were to make a recommendation on which standards to purchase, I would probably purchase 15.2 because it has the most complete. It has more information in it than it does on 15. And I would also purchase ASHRAE B52 2023 for your most updated standards. And that is it for me tonight. I am sorry I had to go through it so quickly. It is a huge topic. It is a huge topic, and there's so much more to know about this. But yeah, thanks for your time.